This is the very first lecture of a lecture series on the distance set problem. We'll begin with a theorem proved by Steinhaus in 1920 out of its beauty. So in 1920, Steinhaus raised this theorem out of almost nothing. And by almost nothing, I mean it's Sierpinski's work on a rather simple problem, which is solving the Cauchy equation in the space of measurable functions. It's pretty much just dirty work, so I'll just put it in chapter 0 in a separate video when we have time to do so. Okay, before giving a proof to the following theorem, let's go through the statement pretty briefly. So, for all measurable subsets of R with positive Lebesgue measure, its different set, defined in this manner, contains an open neighborhood of the origin. So our proof begins with the following lemma. The lemma is pretty much similar. It imposes some condition to the Lebesgue measure of some subsets. So the lemma is like this. It's also for any Lebesgue measurable subsets with positive measure of a closed interval AB. There exists an open interval I such that the Lebesgue measure of the intersection is greater than something times the Lebesgue measure of the interval, and the proof should have appeared in the real analysis homework of many. So let's go through it pretty quickly. So we do it by contradiction. Suppose not, then there exists some gamma 0 such that for all open intervals I, we have that right here. The Lebesgue measure of the intersection between A and I is always smaller than 1 minus gamma 0 times the Lebesgue measure of I. So yeah, this is what we have. And then let's make use of something which is the outer regularity of the Lebesgue measure. We could find a family of open intervals so that they form an open cover and it is just slightly larger and what would happen? The Lebesgue measure of A is actually the Lebesgue measure of the intersection of A and something which covers it up. And to break it apart, we use some basic rules of set theory and some basic inequalities of measure theory. Okay, and now this is the break point. We have that we have from the assumption above, we have that this thing is bounded, everything like this is bounded by one, times one is bounded by 1 times gamma 0, and the big measure times the big measure of the open interval. And then what do we have is that this thing is also bounded. This thing is actually bounded by 1 plus anything. Oh, for all epsilon greater than 0. I've got it. Okay. And let's take epsilon equals to 1.2 gamma 0, and then it uses something like this, making use of the difference of two square identity. Hey, it ends up with something like this. But here, this is positive. So this thing is actually positive, right? And then, so this thing should be smaller than 1. So one thing is smaller than something, is less than 1 minus multiplying by it, and that is impossible, right? Okay. And the lemma is proved. And then we are making use of a second lemma, which is like this. So we are trying to show that the intersection of certain translations is non-empty. So we are having a very weird delta here, but we're going to show that this delta actually has its meaning. So let's go. Again, we are using contradiction. We say suppose it's not. And then what do we have now? Before doing something else, let's do some manipulation to the Lebesgue measure. For example, 2 times the Lebesgue measure of A is actually the Lebesgue measure of A union x plus A, and this is by the translational invariance. Okay, invariance under translation, which is something that we do want. And then, okay, let's go. This is I union x plus I, because it is obvious that the Lebesgue measure of A is smaller than the Lebesgue measure of I, since I've given that A is a subset of I. Okay, so let's remove all these. And we note the following facts. Delta, so firstly, delta is smaller than the Lebesgue measure of I, as you could see, since this thing should be smaller than 1. Okay, so what's the second thing that we note? We have that, by this fact, we have that the Lebesgue measure of x plus I union I is actually the Lebesgue measure of I plus x, because this is pretty obvious. This is an interval, and then you translate it by x, and the length is, this is the Lebesgue measure of I, and this is x. Yeah, and then by the assumption, we have that this thing will be smaller than the Lebesgue measure of I plus delta, which is smaller than 2 plus delta. Yes. And then let's consider the following inequality. And then merging these two inequalities together, we will have that 2 times the Lebesgue measure of A is smaller than the L1 measure of I plus delta is smaller than plus delta, and adding this delta together, we actually have it is actually 2 alpha times. It's actually 2 alpha times the Lebesgue measure of I. Smaller than. Then what do we have? There exists some alpha such that this thing holds, which by assumption and the previous lemma is impossible. And contradiction arises. Okay, so let's do the theorem proper. Since there exists some x0 such that x0 is a subset of x plus a, and x0 is an element of a. And equivalently, there exists some a from the set big A such that x0 is of this form. Hence, what do we have? X is actually x0 minus a. As we have that x0 is a subset, is an element of a, and a is an element of a, and we have that x is an element of a minus a. And by the previous assumption, we know that the set like this, which is actually is a subset of a minus a, which yields the theorem that we desire. And that is the proof of the classical Steinhaus theorem.